All right, class, let's take a look at a couple of these examples from the induced stress lesson that you should have just watched. Okay, so the first example asks us to determine the increased vertical stress at point A due to two line loads and a point load. So point A is here, which is 1.5 meters down from the ground surface. We have one line load here, which is 15 kilonewtons per meter. We have a second line load here, which is 10 kilonewtons per meter. The first line load is 2.5 meters from the directly above that location. The next line load is 2 meters further, and then we have a point load P, which is 30 kilonewtons here, which is along the same line here, but it's 3 meters down from the first location. So what we have here is our three different types of loads that are being applied, and we want to, utilizing superposition, determine what the overall increased vertical stress is at point A. So this is going to require us to break this down into three components. So I'm going to go to the next slide here. And we'll first begin by looking at the first line load. And the first line load, let's go ahead and rearrange the image here to allow us to see this a little bit better. So Q equals 15 kilonewtons per meter. And we know that along the x-axis here, we are at 2 meters from that location, and along the z-axis we are 1.5 meters down to get to point A. Okay, and so we want to determine what the change in vertical stress is at point A due to this line load 1. So I'll just put a 1 there. Alright, and so let's go ahead and draw the second line load. In a similar fashion, we have Q this time equals 10 kilonewtons per meter. And we are the same distance, 1.5 meters downward, but we are at 4 meters to get to point A. And again, so we have a change in vertical stress due to the second line load. Okay, now let's look at the point load. And so the point load is something we need to look at from a three-dimensional perspective. So P exists at some location along the ground surface. It has a magnitude of 30 kilonewtons. And if we were to look at this, let's go ahead and change colors here. If we were to look at this from a Cartesian coordinate perspective, we would have x in this direction here, y in this direction here, and of course we continue with z downward here. And if we can look at that now and understand that we are at some location 4 meters along x, we are 3 meters along y, and again 1.5 meters downward. And if we were to look at all of that, point A would be located here. And so again, based upon this information here, we have a radius. Luckily, fortunate for us, this is a 3, 4, 5 triangle. So the radius is 5, and the distance z is 1.5 meters downward. And so now we have all the coordinate system understood. Let's go ahead and calculate what that change of stress is utilizing all three of these. So the change in vertical stress equals, and we'll go ahead and we're going to use the equations. So 2q1 z cubed over pi x1 squared z1 squared, quantity squared, plus 2 q2 z cubed. Z is the same for each, so I don't have to change that notation. Okay, and then we go ahead and look at the point load. 3p over 2 pi times z cubed over r squared plus z squared, quantity to the 5/2 power. So now that we understand all of this, we can go ahead and just plug in the values and determine what this is. Sum of the vertical forces is 2 times 15 kilonewtons per meter times 1.5 meters cubed times pi, or divided by pi, times x1, in this case is 2 meters. Is 2 meters squared plus 1.5 meters squared, quantity squared, plus 2 times 10 kilonewtons per meter, 1.5 meters cubed, divided by pi over x, in this case is 4 meters squared plus 1.5 meters squared, quantity squared, plus 3 times 30 kilonewtons divided by 2 pi times 1.5 quantity squared over, in this case it's 5 meters squared plus 1.5 meters squared times quantity to the 5/2 power. So now that we have all that information in, the change in the vertical stress, plug and chug. You go and put this in your calculator too. Make sure I'm right. I get about 0.825 kilonewtons per square meter plus 0.065 kilonewtons per square meter plus 0.012 kilonewtons per square meter. Add those up, you get 0.902 kilonewtons per meter squared. Now I want you to notice that the first line load has a significant amount of influence on that stress. The second one is much less than a factor of 10, and then the point load is even less than that because of the distance it is away. And so the lateral distance has a major effect on the influence of stress on any given location. So that was the purpose of identifying this particular problem for looking at the addition of all of these values. Now let's go ahead and look at a little bit more complex of a problem. And as we can see here, we have a a footing pad that is 10 feet by 15 feet, and we are asked to calculate the induced stresses and the total stresses at 3 locations due to this new spread footing that is to be constructed on this site. There's a couple of pieces of information that we need to know here. First of all, the load P that is going to be placed on this is 450 kips. The unit weight of the soil is 120 pounds per cubic feet. And we are asked to determine at the center of this pad, at the edge of this pad, and at some distance 5 feet from the corner of the pad. So we must calculate the change in vertical stress at all locations and the total stress at each location. All right. And based upon what we learned in the previous presentation, we should be able to do this fairly easily. All right, let's go to a fresh slide here. And what I want to do, let's go ahead and identify this from each point. So let's go ahead and look at point A first. And point A is at the center of the pad itself. And so what we're looking at here is 10 feet by 15 feet. Point A is at the center, and it's not a square, so we cannot use the isobars or stress bulbs from the textbook. So what should we do? Well, we'll go ahead and look at the Navy charts. And the Navy charts require us to look at the stress below a location at the corner. So we must break this into 4 different squares because that point is at the center of this footing pad. So we have 1, 2, 3, 4 different squares, and all of those squares have the point that we're trying to analyze at the corner of each of those. And so this becomes pretty convenient because now the distances for each one of those is 5 feet by 7.5 feet. And that's the same for each one of those 4 squares. So that makes things pretty convenient. So now what we want to do is, based upon this geometry, we can go ahead and look at what the values are on the Navy charts. So that being said, let's go ahead and first write down or recall that what Z is. Z is 10 feet. B for each one now is the smaller of the 2 values, so B must be 5 feet, and L must be 7.5 feet because it is the longer of the 2. And now that we have Z, B, and L identified, we can go ahead and determine what M is. And remember, M is B, the short distance, over Z. And in this case, that's going to be 5 feet divided by 10 feet, which is 1/2. And N is L over Z, which is 7.5 feet over 10 feet, which is 0.75. And now that we have that information, we can go to the Navy chart, which is on this next slide here, and we can identify where M and N are. So M, if you recall, was 1/2, and M is at the bottom here. So M is 1/2, and I'm going to go ahead and draw a line along this all the way up. And now N was 0.75, and that is halfway between these two right here, 0.7 and 0.8. So I'm going to draw a line. It's not going to be perfect here, but should work okay right about there. And where those two cross becomes our influence factor. Influence factor at this case is, it looks like it's just a little bit more than halfway between 0.1 and 0.11. So I'm going to call this 0.107. Everybody okay with that? So let's go back up to our previous slide, and we have identified I as 0.107. All right, so now that we have that information, let's go ahead and calculate what our change in vertical stress is for point A. Change in vertical stress of point A, in this case, is simply I times 4 of them, because remember the I will be the same for each of those shapes, and there are 4 shapes, multiplied by Q. Q is the stress that is applied due to the load of the entire footing. So this is 0.107 times 4 times, now the stress is P over A, so that's 450,000 pounds, divided by the area, 15 feet by 10 feet, which turns out to be 3,000 pounds per square feet. 0.107 times 4 times 3,000 pounds per square feet. And so our change in vertical stress at point A equals 1,284 pounds per square feet. That's our change in vertical stress at point A. But it also asks us for the total stress at point A. So it also asks us for the total stress at point A. Well, to calculate the geostatic stresses at point A, the initial geostatic stress at point A, we need to know what the unit weight of the soil is. We assume that the unit weight is the same throughout. I don't see any indication of groundwater table. So the geostatic stresses in this case are just the unit weight of the soil multiplied by the depth at which that point we're analyzing is located. So that equals 1,200 pounds per square feet. So the total stress in this case is our initial stress plus our change in vertical stress at point A. Total stress is going to be 2,484 pounds per square feet. Okay, now let's look at point B. Point B is looking at a location at the center but on the edge of the footing. Remember, our dimensions here are 10 feet by 15 feet. And so what we want to do here is we want to analyze this. Again, we can't use the isobars because it's not a square. So let's go ahead and figure out a way to make the geometry such that we can break this down, and each square that we're analyzing is at a corner, and we can use superposition to determine that. And that would be just cutting it right in half. And now point B right there is at the corner of each side of this. So now we have one dimension here of 7.5 feet, but the other side remains 10 feet. So that being the case, we now can go ahead and determine what our M and N are. Z remains the same at 10 feet. B now becomes 7.5 feet. And L is 10 feet. So now we can determine what M is. Remember, M is B over Z. And it's 7.5 feet divided by 10 feet, which is 0.75. And N is L over Z. In this case, it is 10 feet by 10 feet, or 1. And now that we have M and N, let's go ahead and back up to our Navy chart. And we can look at, go ahead and use red for part B. And we can look at, remember, M this time was 0.75, which is right here. Draw a vertical line that actually looks like a vertical line in this case. And N was 1. So we are looking at a value that just looks like in between 0.15 and 0.16. So we'll call this 0.155. So now that we have that information, we go ahead and say that the influence for B is 0.155. And now we can determine what our change in vertical stress is at point B. And that is, this time we have 2 times I sub B times our stress Q. It is 2 times 0.155. Our stress Q is again 3,000 pounds per square feet. And that totals 930 pounds per square feet. That's our change in vertical stress at point B. Again, we want to calculate also the total stress at point B, and that is the calculation of the initial stress at point B plus the change in vertical stress at point B. Well, the initial stress at point B is the same as it was at point A because the unit weight of the soil is the same, the depth is the same, so it's again 1,200 pounds per square feet plus 930 pounds per square feet. So the total stress at B will equal 2,130 pounds per square feet. Okay, so to compare the center of that footing pad to the edge of that footing pad, we are looking at a change in about 300 pounds per square feet. 350 pounds per square feet. That's pretty significant. All right, so it asks us to do one more. So let's look at point C. Now point C is quite unique because it is outside the footprint of the footing itself. So let's go ahead and draw a picture here. Always draw a picture. And so we know this is the initial size of the footing. 10 feet by 15 feet. But this time point C is located outside the footprint along one of the corners. And so what we want to do this time is we want to add a portion of the footing that doesn't exist. And so what we're trying to do here is say that we have a large footing where point C is at the corner of this large footing, and then we want to subtract this smaller portion that is not beneath that footing from that influence to get now the actual influence for point A. So I'm going to call this green portion here 2, shape 2, and the blue portion here shape 1. All right, so let's go ahead and look at now the dimensions for shape 2 and shape 1 because they are different. Okay, but remember point C is at the corner of both of those shapes. So the dimensions of 1 go like this. Z again is 10 feet. B is now not 10 feet, but 15 feet. Because remember, this part here is 5 feet. And then L is also 15 feet. It's now a square, but it's at the corner. Okay. The dimensions of shape 2, Z again is 10 feet. B this time, the smaller, is 5 feet, and L is 15 feet. And so now we want to determine M. Remember, M is the B over Z, which in this case is going to be 5 over 10, or 1/2. N is L over B, which is 15 feet over 10 feet, which is 1.5. M for the first shape, again, is B over Z. Which is 15 feet over 10 feet, which is 1.5. And N is L over Z, which is the same. I apologize for this. This should be Z. Okay, so going back to our Navy charts, go ahead and see how yellow shows up. So for the first shape, we are at 1.5 for both M and N. 1.5 is way up here for N, right here. And so that gives us an I for the first shape for C of 0.205. And let's use orange for the second shape. And remember, M for the second shape was 0.5, which is this yellow line here, and that crossed 1.5, which is halfway between these here. Which is right about here. And that gives us a value of right about just under 0.13. So we'll call it right about 0.13 or so. Might be 0.128. That is I2 of C. And we'll use these two values here. Got a little crowded. I probably should have used a fresh shape, but you don't have one, so I wanted to keep that the same. And so now we can go ahead and write down our influences here. Influence for the first shape here, if you recall, was 0.205. And the influence for the second one was 0.13, or close to it. Okay, so now let's go ahead and set up our equation for the change in vertical stress for point C. Well, this time what we want to do is we want to take, because these are quite different, and what we want to do is we want to look at our I of 1 times Q minus our I of 2 times Q. Or we can just take I sub 1 minus I sub 2 times Q. And that is 0.205 minus 0.13 times 3,000 pounds per square feet. Our change in vertical stress at point C turns out to be 225 pounds per square feet. And so our total stress at point C is just our geostatic stresses at point C, which is the same, plus our change of vertical stress at point C, which is 1,200 pounds per square feet, plus 225 pounds per square feet. So our total stress is 1,425 pounds per square feet. And as you can see, now that we are outside the footprint of that footing and at the corner, the amount of stress is significantly lower than point B and point A. And so that's how you calculate the amount of stress, induced stress, due to a footing at various locations. Now I think you're ready for your homework.